With this video, I would like to show you the setup of a simple standard shape optimization task. The example used is a hub as you can find in wind turbines. Well, to start with the optimization task, you will first have to define your analysis model and load it into Abaqus CAE. This should be available as fully defined Abaqus input deck. Here the hub is realized as a symmetric model with a 120-degree symmetry. So, to set up the optimization task, you can create here a shape optimization task, which will be used to reduce stress peaks at the surface of the hub. First, you have to define your design area. That's the area, the group of nodes which are allowed to be modified by the optimization. You can define additional constraints. For example, you can freeze your boundary condition nodes and specify a certain smoothing region which is used to ensure a constant or a good mesh quality for the analysis. Here, additional settings can be made for the mesh smoothing algorithm. Normally, the default values are quite good, but you could also modify them mostly at the cost of a higher runtime. Other advanced settings are available for the optimization task, which you could look up in your documentation. The first step to create your optimization task would be to define your design responses. These are values which characterize the quality of your design. In this case, we choose the maximum Vermeer's stress for our optimization. First, we have to choose our design response region, in this case the design node area, for which we will calculate or extract our design response. So we choose the Vermeer's stress here, and in the second step we will have to choose for which load scenarios the Vermeer's stress is extracted. In this case, we take the maximum value over all steps and load cases in the model. So once this design response is extracted, we can set our objective. And the objective will be to minimize the maximum Vermeer's stress. Thus, we will assign here our predefined design response, Vermeer's stress extracted for all load cases, and set the target to minimize this design response. So optionally, we could define a volume constraint here, which we will not do, but we should certainly create some geometric restrictions. The first of them, to ensure the rotational symmetry. That means to keep the cyclic repetition of the segments here for the area of the design nodes. That is the area which is changed during the optimization. And first we have to define an axis for the cyclic symmetry. We could define it by defining 2 points of the axis on the axis, and we have to set the repeating segment size by 120 degree here. So, a second geometric restrictions which is often used here is we could define node fixations to ensure, for example, the connection to adjacent parts. In this case, we choose a certain group of nodes which is not allowed to change in all 3 static directions. So once our optimization task is completely defined, we can set up our optimization job. And to this end, we will create the optimization process here and assign the predefined optimization task to the process. In this process definition, we can set some parameters, for example, which results are to be saved and so on. And now we can start our job as usual, submitted in Abaqus CAE. During the optimization run, we can monitor the evolvement of the job or of the result. That means we can have a look into the values of the objective function. We can create a plot of the objective values, how the maximum Fermi stress is decreased over the several cycles. And once the optimization job is completed, we have for each iteration the Abaqus results available here in the job folder, and we can combine them for easier post-processing to one single ODB. We choose the results of interest, for example stress, but the optimization results are already pre-selected. So this combined ODB is now available for detailed post-processing. We could switch to this visualization module and have a deeper look into, for example, the optimization displacement and run through the single iterations of the optimization to see how the nodes are displaced during this process. And finally, we could check the stress distribution and see how the stress peaks are diminished during this optimization.